I am quoting directly from CERN's official website. At the LHC accelerator, the largest detector, ALICE, detected the transformation of lead into gold. This is not an interpretation, but an official statement. As a result, the news that gold was produced at CERN has recently spread rapidly across popular science platforms. It didn't stop there. The story also made headlines in all the tabloid newspapers. The idea that something like this could actually happen in a massive 20 billion euro laboratory at the heart of particle physics may seem impossible at first glance, especially for science enthusiasts like us. But when we looked deeper into the details of the reports, we realized that such an event had indeed occurred. However, knowing only part of the truth can be misleading. And aware of this, we wanted to take a much closer look at the topic. The first thing we did was to check if there was a scientific paper published on this subject. And indeed, we found a paper published in a prestigious journal like Physical Review Letters discussing this very topic. So, there was real experimental evidence showing that gold had indeed been produced. One of the greatest dreams of medieval alchemists was to transform an ordinary metal, like lead, into a precious one, like gold. The idea was so captivating that even Nobel Prize-winning author Gabriel Garcia Marquez used it as the starting point of his famous novel, 100 Years of Solitude. This pursuit, known as chrysopoeia, meaning the transmutation of all metals into gold, was largely inspired by the fact that lead was abundant, while gold was beautiful, rare, and had almost the same density as lead. Or perhaps it was simply the idea of getting rich quickly. At this point, we must give credit to the alchemists. They left us a valuable curiosity about understanding the nature of matter, a curiosity that eventually led to the birth of modern science in the 17th century. Alchemy gave way to chemistry. Magic gave way to experimentation. Legend gave way to theory. And in this way, what was once seen as a disappointment became one of the cornerstones of science. In fact, if you could transform lead into gold on an industrial scale at a low cost, the value of gold would equal the value of lead. Calculated at today's prices, the price of 1 ounce of gold would suddenly drop to around $69. Most likely, medieval alchemists never considered this economic reality. But let's be clear, such a thing is not possible today either. And it wasn't just alchemists. Modern scientists also attempted to achieve this transformation. In 1930, researchers succeeded in producing gold from lead in a laboratory for the first time. But the cost of the process reached billions of dollars for just 1 gram of gold. That's why producing gold from lead never became an industry. So, where did these recent headlines about gold being produced at CERN come from? In fact, the origin of these stories lies in a misunderstanding of the scientific work being carried out at CERN. CERN operates a giant particle accelerator with a 27-kilometer underground tunnel, colliding millions of particles every day at speeds close to the speed of light. But their goal is not to produce gold. Their goal is to understand the smallest particles in the universe and how they behave. Through the collisions in this massive accelerator, scientists are investigating the most fundamental building blocks that make up the nature of the universe. In other words, the work being done at CERN is not about manufacturing gold, but about uncovering the tiniest components of matter to understand how the universe works. Particles are being collided at CERN because scientists want to understand the fundamental building blocks of nature and the interactions between those building blocks. Everything we see in our daily lives exists because atoms and the particles beneath them behave according to certain rules. To uncover what those rules are, scientists accelerate particles to nearly the speed of light and make them collide head-on. But why do they need to collide these particles at such incredibly high speeds? Because revealing the tiniest building blocks of the universe is simply not possible at ordinary speeds. When particles are accelerated to near light speed, the energy they carry reaches extraordinary levels. Without such high-energy collisions, particles would merely bounce off each other without ever breaking apart. High speed is essential for new particles to emerge, because high speed means high energy. And this energy, according to fundamental physics laws like E equals mv squared, creates the conditions for new particles to appear. In fact, this is exactly how the Higgs particle and the Higgs field were discovered. Unfortunately, all these groundbreaking scientific achievements have never received as much attention as the sensational headlines claiming that gold was produced at CERN. So, why do we collide particles? Actually, It's quite similar to taking apart a clock to understand how it works. To make it even more relatable, imagine taking two mechanical clocks and throwing them at each other at high speed. Of course, a light tap wouldn't be enough to break them apart. You would need to crash them together with significant force. In the same way, at CERN, scientists examine the smaller particles and the energy released when particles collide at high speeds in order to uncover how nature works. Through these studies, they gather clues about the formation of the universe, dark matter, the Higgs particle, and other great cosmic mysteries that we still haven't fully solved. In short, all the collisions happening at CERN represent one of the greatest experimental efforts in human history to understand the fundamental laws of the universe. But is turning lead into gold part of this process at CERN? Surprisingly, the answer is yes. But transforming lead into gold is not the real goal here. It happens as a natural byproduct of the high-energy collisions being conducted. Just like when you smash two mechanical clocks together, you don't only break them into pieces, you also hear a noise. Similarly, the transformation of lead into gold is not the main objective of these scientific experiments, but rather one of the many short-lived byproducts that appear during the collisions. The extremely high-energy lead nucleus collisions conducted at the LHC can create a state of matter known as quark gluon plasma, which is believed to have existed just a millionth of a second after the Big Bang. This plasma is defined as the most primitive and energetic form of matter, in which the most fundamental building blocks of particles are freed. And colliding lead nuclei is a highly effective method to generate this structure. One of CERN's primary goals is to recreate these earliest moments in a laboratory setting in order to test theories about the Big Bang. That's why CERN is not colliding lead to turn it into gold, but to study the universe's first moments. The lead nucleus used in these experiments is the central core of a lead atom, made up of 82 protons and around 125 neutrons. So, how does this process work? First, lead atoms are extracted from specially prepared sources of lead gas or vapor. These atoms are ionized, meaning their electrons are stripped away, leaving behind only positively charged lead nuclei, or ions. These ions are then transferred into pre-accelerators using electric and magnetic fields. The devices used at this stage are called linear accelerators. In other words, the journey of lead atoms begins here. Next, the lead nuclei, having reached a certain speed, are transferred into the 27-kilometer-long LHC tunnel. Inside this tunnel, in a vacuum environment, they are accelerated in opposite directions within blue tubes lined with superconducting magnets. While this might sound simple, the process requires extremely advanced technology. Because while particles normally move in a straight line when accelerated, it takes the perfect coordination of 10,000 superconducting magnets to bend their path in a circular tunnel and bring them to collide. Finally, with the help of special areas called RF cavities, these nuclei are continuously pushed by electric fields to gain even more speed, preparing them for the collision. The goal is to accelerate the lead nuclei to 99.9999993% of the speed of light. That means about 299,792,437 meters per second. In other words, just 21 meters per second slower than the speed of light. At this speed, the effects on time are truly remarkable. Time slows down by about 86%. If a traveler could move at this speed for 1 year, by the time they return to Earth, only 1 year would have passed for them, while 84 years would have passed on Earth. And now, two lead nuclei, traveling at nearly the speed of light, come face to face, ready to collide. Normally, in this collision, the nuclei shatter apart, and the new particles produced are detected by CERN's advanced detector systems, providing billions of data points. But sometimes, things don't go as expected. Instead of colliding head-on, these two nuclei sometimes just glance off each other. In fact, this glancing interaction is not something scientists specifically aim for. However, it still occasionally happens. And in those moments, the extremely powerful electromagnetic field of the lead nucleus, compressed into a thin pancake shape perpendicular to its direction of motion due to its near light speed travel, comes into play. This ultra-short-lived compression generates a very brief photon burst, triggering a process known as electromagnetic dissociation. The photon produced interacts with the approaching nucleus, stimulating vibrations in its internal structure. This causes a few protons and neutrons to be knocked out and ejected. For example, gold consists of 79 protons, while lead has 82 protons. So if just 3 protons are knocked off a lead nucleus, what remains is a gold nucleus. And during these glancing encounters, this exact process sometimes occurs, resulting in the creation of gold from the lead nucleus. Normally, scientists analyzing data from these collisions are used to tracking thousands of different particle traces. But in some data sets, they notice just 1, 2, or 3 particles emitting signals. When these unusual events were carefully filtered and reanalyzed, a fascinating pattern emerged. According to the collected data, when 1 particle is observed, thallium is produced. When 2 particles are observed, mercury appears. And when 3 particles are observed, gold is formed. You might wonder how such tiny changes can even be detected. At this point, a graph included in the scientific paper clearly demonstrates just how precisely this process can be measured. In the graph, the vertical axis represents the likelihood of these glancing events occurring. For example, thallium production from the loss of 1 proton appears to occur with a much higher probability than the others. Gold production is less frequent than thallium, but still occurs at a measurable rate. The least likely product is hafnium. The ALICE detector, capable of detecting even these extremely rare events, once again proves its remarkable sensitivity. Measurements show that at the ALICE collision point of the LHC, approximately 89,000 gold nuclei are produced every second. So, you might be wondering, where do all these gold nuclei actually go? In reality, these gold nuclei, after the collision, are ejected with extremely high energy. These ejected nuclei then smash into the LHC's beam pipe or the beam collimators, where they immediately break apart, dissolving into single protons, neutrons, and other particles. In other words, the gold that is produced only exists for a very brief moment before it disintegrates and vanishes. So, how much gold has been produced so far? According to the analysis of the ALICE experiment, during Run 2, between 2015 and 2018, around 86 billion gold nuclei were created. Since the beam intensity of the LHC has been continuously increasing, this number nearly doubled during Run 3, reaching a total of 258 billion nuclei. However, despite these staggering numbers, they amount to less than 1/12 billionth of a gram of gold. Even if you collected all that gold, its value would be just about 0.0000034 cents. So, in the end, while the dream of medieval alchemists may have technically come true, their hopes of getting rich have once again been dashed. Thank you for supporting our channel by subscribing. Your comments make our community even stronger. See you in the next video.